So the paper is called Can LLMs Perform Deep Technical Comprehension of Computer Architecture Papers by Nishant Agarwal and a team from UW-Madison and NVIDIA.
Right, and we are skipping the intro today because the core insight here is just massive. I mean, the bottom line is that standard LLMs are honestly terrible at deeply critiquing technical papers.
Yes, they basically just summarize, right?
Exactly. But if you structure them into a multi-agent pipeline, which they call Gauntlet, with independent expert personas and this adversarial synthesis stage, they can actually beat human graduate students.
Which is wild. Like out of 20 dense architecture papers, this AI pipeline beat human analysis 15 times.
Yeah, 15 out of 20. It extracts mechanisms, spots critical flaws, and it totally refuses to just give you a generic summary.
And that is exactly why we are covering this on today's episode of AI Paper Slop.
Huh.
I mean, we know you're all struggling to keep up with the fire hose of ML and architecture research.
Oh, it is completely unmanageable for anyone building hardware right now.
Right. So our goal for this deep dive is to unpack exactly how this gauntlet structure works, why it beats humans at critical rigor, and also where it still hilariously fails.
Because it definitely does still fail.
Oh, absolutely. So you can hopefully apply these principles to your own research triage. But let's start with the baseline problem. Like if I take a massive paper, drop it into Claude Opus or GPT-4 and use a fancy chain of thought prompt, I just get a very fluent wall of text.
Yeah, a confident wall of text that completely misses the actual underlying mechanism.
Exactly. Why does a powerful frontier model fail so consistently at this?
Well, the failure is structural. It really comes down to something called context window collapse.
Context window collapse. Okay, break that down for me.
So when you feed a complex technical paper into a single LLM prompt, even if you explicitly ask it to, think step by step, all of those reasoning steps share the exact same context window.
Right. It's all just one big bucket of memory.
Yeah. And the model's underlying training, especially the RLHF, the reinforcement learning from human feedback, that heavily biases it toward being a helpful, coherent assistant.
I see. It fundamentally wants to output a unified narrative.
Exactly. It wants to tie everything up with a neat little bow. Think of a shared context window like a corporate committee meeting where everyone is sitting in the exact same room.
Oh, that's a great analogy.
Right. So if someone points out a brilliant microarchitectural trick, but then someone else spots a glaring, catastrophic flaw in the simulation methodology, the social pressure of the room kind of forces a compromise.
Yeah. Nobody wants to be the one ruining the vibe of the meeting.
Exactly. So these distinct critical concerns collapse into a generic middle-of-the-road consensus. The AI smooths away the tension just to present a clean summary.
That makes perfect sense. The model literally averages away the most important contentious parts of the research. So how does the UW-Madison team actually bypass that internal consensus?
By physically or, architecturally separating the committee. Which brings us to phase 1 of the Gauntlet pipeline.
The independent review stage.
Right. They built this using Claude Opus 4.5. They give it an 8,000 token context limit, which is plenty to comfortably fit dense papers, but they make a crucial adjustment to the model's parameters.
The temperature setting, right?
Yeah, they drop the temperature all the way down to 0.3.
So I always hear about adjusting temperature, but mechanically, what does dropping it to 0.3 actually do inside the model for a task like this?
Well, temperature basically controls the probability distribution of the next token the model predicts. So a higher temperature flattens that distribution.
Meaning it picks less likely words.
Yeah, which we perceive as, creativity or, in the worst cases, hallucination. So by dropping it to 0.3, you are sharply narrowing that distribution. The model becomes much more deterministic and rigid.
You're stripping away its desire to be a creative storyteller.
Exactly, because for reverse engineering silicon architecture, you don't want a story. You need cold, analytical rigor.
Okay, so you have this highly analytical model. But you mentioned committee earlier. How are they deploying these rigid models?
So Gauntlet spins up 5 completely independent AI agents to read the paper's PDF. And the absolute unbreakable rule of phase 1 is that these agents have zero visibility into what the others are doing.
I love the mechanics of this. It's basically like assembling the ultimate slightly hostile thesis defense committee, right?
That is exactly what it is.
You lock them each in separate soundproof rooms and force them to evaluate the work in total isolation. So who actually makes up this panel of 5?
Well, 3 of the agents are fixed. They show up for every single paper. First, you have a persona called Dr. Microorg.
And what's their specialty?
This agent's prompt explicitly forbids it from caring about benchmark results or high-level applications. Its sole directive is to reverse engineer the hardware mechanism at the bit and date level.
Oh, wow. Okay, so very low level. Who's next?
Second is profess workloads. This agent completely flips the script. It ignores the hardware elegance entirely and acts as a ruthless auditor of the evaluation.
So it's looking at, like, benchmark selection and baseline fairness.
Exactly. Statistical significance, all of that. It's the ultimate skeptic.
Every peer review needs one of those, honestly. And the third fixed agent.
The third is profess sim tools. This one focuses entirely on simulation fidelity, basically asking if the results could actually be reproduced in the real world.
Okay, so those three form the foundation. But I saw in the methodology that they don't just use generic reviewers for the last two slots. The system actually does something dynamic.
Yeah, there's an initial topic detection step. Gauntlet reads the abstract first, and then it matches the paper against a stored library of about 90 highly specialized expert personas.
90 personas, that's a huge library.
Yeah, so if a paper is introducing a new sparse tensor accelerator for machine learning, the system automatically pulls a sparse computation specialist from the library.
And maybe like a memory bandwidth expert to go with it.
Exactly. Those two domain-specific personas join the three fixed professors to round out the panel of 5.
Okay, I have to play devil's advocate here for a second. By forcing these AI models into incredibly narrow, isolated personas, don't we risk them missing the forest for the trees?
What do you mean?
Well, if Dr. Mike Roach only looks at gates and Profaf Workloads only looks at data tables, nobody is looking at the paper as a holistic piece of research. You just end up with 5 fragmented lists of complaints.
You've highlighted the exact vulnerability of phase 1. If you stopped right there, you would just have a disconnected pile of observations.
So how do they fix it?
That is the entire reason phase 2 exists. Phase 2 is the adversarial synthesis stage.
The adversarial synthesis, okay.
Yeah, so once all 5 independent, isolated reviews are generated, they are dumped into a brand new prompt managed by a synthesizer model.
And do they keep that synthesizer model at the super rigid 0.3 temperature?
They actually bump the synthesizer's temperature up slightly to 0.5.
Wait, really? Why the increase? If we want rigor, shouldn't we keep it cold?
Well, synthesis requires a wider semantic search space. The model needs just a little bit more flexibility to weave competing concepts together.
I guess it has to find relationships between totally different domains, right?
Exactly. But here's the kicker. The defining instruction for the synthesizer, the golden rule of this entire pipeline, is to explicitly preserve disagreements.
Oh, preserve them. Do not average them away.
Exactly. If Dr. Michael Roach writes a glowing review of a novel cache design, because the bit-level math is beautiful, but Professor Workloads flags that it was only tested on highly favorable sequential memory benchmarks, the synthesizer cannot just say the design is promising, but needs testing.
Right. It's forbidden from writing a polite conclusion.
Yes. It is instructed to pit the two viewpoints against each other. It actively surfaces the tension.
So it artificially recreates the exact debate you would want your senior engineers to have in a reading group.
Exactly. And the final output is highly structured. It generates a consolidated reading guide with 4 strict sections.
What are the sections?
Section 1 is the whiteboard explanation, can it explain the core mechanism as if drawing it on a whiteboard? Section 2 is the key insight.
Basically the aha moment that makes the design work.
Right. Section 3 is the evaluation critique. And Section 4 is arguably the most valuable. It's titled, What the Authors Didn't Tell You.
Oh, I love that. The skeletons in the closet, the buried assumptions.
Exactly.
Well, the theoretical structure of this adversarial pipeline sounds incredible. But, theory is cheap in AI. When you actually put this up against highly caffeinated, deeply trained human experts, does it really catch things they miss?
Let's talk about the showdown. The researchers set up a blind trial. They recruited 10 graduate students who were active, publishing researchers in computer architecture.
Okay, so these aren't just random undergrads.
No, these are serious researchers. They assigned these students 20 dense, complex mechanism papers drawn from upcoming top-tier conferences, specifically ISCA 2025 and HPCA 2026.
Just to anchor that for anyone listening who might be outside the hardware space, ISCA and HPCA are the absolute gold standard conferences for computer architecture. Getting a paper accepted there requires immense rigor. Oh, yeah. These are not simple blog posts. They are mathematically dense hardware blueprints. So each human student wrote an analysis answering the exact same 4 questions that Gauntlet produces.
And then they brought in judges.
Yep. An independent panel of blinded judges, who were other senior researchers, scored the machine's output against the human's output across 5 different dimensions.
The scoreboard here is what caught everyone's attention. I mean, out of 20 head-to-head comparisons, Gauntlet won 15 times. The humans won 4 times, and there was 1 tie.
A 15-4 blowout in a highly technical, specialized domain. It's crazy.
Where was the AI actually drawing the most blood? Like, what specific metric did it dominate?
Gauntlet utterly dominated on a metric the judges called critical rigor. And the statistical advantage there was massive. The p-value was less than 0.01.
Wow. So it wasn't even close. Not at all. When the human grad students critiqued a paper, they often resorted to generic academic feedback, like, the evaluation could be strengthened by adding more hardware baselines.
Right, the classic peer review filler.
Exactly. But Gauntlet does not do generic. Gauntlet explicitly named the specific missing baselines, the untested parameters, and the mathematical sleights of hand that the humans just glossed over.
We really have to unpack the Q-tenon example because the specific catch here is mind-blowing to me.
Oh, the quantum paper, yeah.
Yeah. Q-tenon was proposing a new quantum classical hardware accelerator. What did Gauntlet catch that the humans read right past?
So this is professed workloads running its keep. The authors of the Q-tenon paper claimed their new architecture achieved a massive 5,000x communication speedup.
5,000 times. That's a headline-grabbing claim.
Right. And to prove this in their evaluation, they compared their architecture against a baseline system using an Ethernet-connected FPGA, an older reprogrammable chip setup.
And an Ethernet connection has a latency of roughly 10 milliseconds, right?
Yes. But Gauntlet's synthesis step flagged a massive domain discrepancy. It pointed out that in the real world, modern quantum systems, like the ones built by IBM or Google, do not use Ethernet to communicate.
Wait, what do they use?
They use standard low-latency links, specifically PCIe or CXL protocols, and those links operate with latencies in the range of 100 nanoseconds to 1 microsecond.
Oh, wow. So 100 nanoseconds versus 10 milliseconds.
Exactly. So the AI is essentially saying, your 5,000x speedup is mathematically accurate, but you are comparing a Ferrari to a bicycle instead of another car.
That is brutal.
It did the math right in the critique. It showed that if the authors had used a realistic PCIe baseline, that 5,000x speedup instantly shrinks down to just 100x to 1,000x speedup.
Which is still a valid improvement, obviously, but it completely changes the scale of the contribution. And the human reviewers entirely missed the baseline mismatch.
Entirely missed it.
See, this makes me reflect on my own reading habits. I mean, is the AI actually demonstrating a higher level of intelligence here? Or is it just infinitely better at holding a massive database of latency specs in its active working memory without suffering from cognitive fatigue?
That is a crucial distinction, and the authors actually address it.
Yeah.
They do not claim the multi-agent pipeline is smarter in a sentient way. They argue that multi-perspective synthesis leverages perfect recall. It catches what a single human reader reliably misses just due to sheer cognitive load or domain unfamiliarity.
Because as a human reader, unless you work specifically on quantum interconnects every single day, you might see Ethernet FPGA and just accept it to keep the reading flowing.
Right, but the AI has the spec sheet for the entire semiconductor industry loaded in its immediate recall.
Okay, but we have to acknowledge that the human reviewers still won 4 of those matchups. A 15-4 win rate means the machine is vulnerable. When it failed, why did it fail?
The failures are arguably the most fascinating part of the study. They really reveal the boundaries of current LLMs. They generally fell into 3 categories: trust, teachability, and triage.
Let's start with trust. What happened there?
The first major failure mode is what we can call the confident hallucination. This happened during the review of a paper called Magic Cache.
Oh, the dual mode cache array design.
Yes. In its What the Authors Didn't Tell You section, Gauntlet confidently asserted that the paper's novel bitline computation imposed a massive 60% latency tax on every single cache access.
So it claimed every read would take, 1.6 nanoseconds instead of the standard 1.0 nanosecond?
Exactly.
But wait, wasn't the entire physical design of that chip built specifically to avoid that exact problem?
Yes. That was the fatal flaw in the AI's reading. The core contribution of the Magic Cache paper is a specialized per-line gate that intentionally keeps ordinary reads on a fast 1.0 nanosecond path. Only complex computational accesses get routed to the slower 1.6 nanosecond path.
Wow. So Gauntlet completely missed this fundamental structural bypass.
Completely missed it. Yet it stated its totally wrong conclusion with absolute, unshakable confidence.
That destroys trust immediately. I mean, the human judge evaluating that matchup noted that Gauntlet's review was actually much deeper in other sections, but because it hallucinated a fatal architectural flaw out of thin air, they just threw the whole review out.
It's like having a brilliant coworker who occasionally fabricates data with a completely straight face, you know? You simply cannot rely on their output without double-checking everything.
Absolutely. Okay, what about the second failure mode? You mentioned teachability.
Right. This surfaced in the evaluations of two papers, Profit and LLBPX. Gauntlet correctly extracted the mechanical descriptions, but it failed to translate or teach them.
How so?
Well, for instance, in LLBPX, the AI just regurgitated an undefined acronym, CID64, without ever explaining what it actually meant in the context of the new architecture.
Oh, so it read like a highly technical gloss that just assumed the reader already had all the context.
Yeah,
But the profit paper example is even better. I really want to dive into the math on that one.
Oh, let's do it. The Profit paper claimed their new design resulted in a 1.6% energy increase in exchange for a 35% reduction in processing time.
And Gauntlet just faithfully reported those two numbers as a net positive.
Right. But the human reviewer stopped, looked at the basic physics relationship between energy, power, and time, and actually recomputed the math.
Because power equals energy divided by time.
Exactly. The human pointed out that if you have a 1.6% increase in total energy, but you are burning that energy in a time frame that is 35% shorter, you have a massive spike in instantaneous power.
Doing the math, that translates to roughly a 56% increase in power density.
A 56% power spike.
That is a profoundly human insight. The human reviewer realized the authors intentionally framed their results using energy to camouflage a disastrous thermal power problem.
Right, because a 56% power spike means that chip is going to melt the motherboard.
Exactly, and the LLM just acts as a pattern-matching engine. It blindly accepted the author's framing. It completely lacked the semantic reasoning to translate those numbers into physical thermal reality.
Which leads perfectly into the third failure mode, judgment and triage. This was highlighted in the evaluation of a paper called LightML.
What happened with the LLM?
So Gauntlet's weakness section for this paper was incredibly comprehensive. It found every possible discrepancy, but it exhibited zero prioritization.
Let me guess. It grouped minor typos right alongside fatal flaws.
Exactly. It placed a trivial complaint about how the authors visualized their analog-to-digital converter power consumption right next to a catastrophic load-bearing flaw.
What was the flaw?
The authors used a completely unvalidated, unproven hardware simulator.
Oh, wow. This, to me, is the skin in the game problem. I mean, an AI doesn't have a budget, it doesn't have product deadlines, and it obviously doesn't deploy physical hardware. It can spot discrepancies because it matches text patterns. But can an LLM ever truly understand which flaws actually matter in the real world? Like, any junior human engineer knows that an unvalidated simulator means the entire paper belongs in the trash.
Right, whereas a wonky power chart is just something you fix in a minor revision.
Yeah.
But the AI weighted them equally.
It's a profound limitation. The machine gives you a highly detailed topological map of every bump in the road, but you still need human expert judgment to decide which of those bumps will actually destroy the suspension on your car.
That's a perfect way to put it.
So we have a pipeline that is incredibly powerful, but lacks physical intuition and prioritization. For any developer or engineer listening right now who works with LLMs, the burning technical question is, why does Gauntlet win 15 out of 20 times?
Is it the structure or the model?
Yep. Is it just because Claude Opus 4.5 is an exceptionally smart baseline model? If I just wrote a really dense 5-paragraph persona prompt, could I get the exact same results without building a whole multi-agent system?
The UW-Madison team anticipated that exact skepticism, so they ran a massive ablation study.
And an ablation study is basically stripping the pipeline down to its studs, right?
Yeah.
To see which specific component is doing the heavy lifting.
Exactly. And they scaled up the data set from 20 papers to 98 papers for this. Since grading 98 dense architecture papers manually is literally impossible, they used Google's Gemini 3.1 Pro as an automated, blinded judge across 3 randomized runs.
And they tested 3 different configurations. What were the setups?
Setup A was a baseline one-sentence directive, simply read and critique this paper. Setup B was the ultimate mega prompt. It was a rich, highly engineered persona instructing the model to act as a skeptical, brilliant computer architect.
Okay, and setup C?
Setup C was the full multi-agent Gauntlet pipeline with the adversarial synthesis phase.
So what did the ablation show?
The full pipeline, Setup C, beat the single, highly engineered persona 96% of the time.
96%, wow.
I mean, think about the implications of that. All three setups use the exact same underlying model intelligence, Claude Opus 4.5. The difference isn't the model's raw capability.
It's the architecture.
Yes. The structural isolation of independent agents forced into an adversarial synthesis phase is definitively the mechanism that generates deep insight. The architecture of the AI pipeline matters vastly more than the prompt wording.
Context window collapse is real, and structural isolation is the cure. That is fascinating. But there was one specific type of paper where the multi-agent system actually underperformed.
Yeah, good catch. The researchers noted that Gauntlet's advantage shrinks dramatically on what they call single-trick papers. They highlight a specific paper called MEM-SOS.
What happens with single-trick papers?
Well, if a research paper is incredibly narrow-like, proposing just one simple, highly focused mechanism running it through a 5-agent adversarial debate actually dilutes the core point.
Oh, I see. For narrow ideas, a single focused reading captures the essence perfectly.
Right. The ensemble pipeline just hallucinates unnecessary complexity because it's trying to find a debate where one doesn't exist.
So pulling all of this together, what does this actually mean for you, the listener, trying to stay afloat in the sea of tech research? Because the authors of this paper make a highly provocative philosophical claim.
They do. They argue that building the Gauntlet pipeline is fundamentally computer architecture research. It's not just generic prompt engineering.
And the logic holds up.
Yeah.
The true innovation here isn't just knowing how to interface with an API. The innovation is encoding deep, domain-specific hardware knowledge into the tool's very structure.
Exactly. Only an expert computer architect knows that you specifically need one isolated persona to stress test data benchmarks and a totally separate blinded persona to audit simulation fidelity. The quality of the final critique is a direct reflection of the domain expertise hard-coded into the pipeline structure.
But the authors are very careful to say this is a tool for navigating the literature, right? Not a replacement for human reading.
Definitely. The neurological connections you make when you struggle through a dense paper cannot be outsourced, but Gauntlet is the ultimate triage tool. Like, if you are crossing into an unfamiliar subdomain of machine learning, it prevents you from being fooled by an unrealistic baseline.
It serves as an incredible calibration tool. A junior engineer can read a paper, draft their own critique, and then compare it to Gauntlet's adversarial synthesis to see exactly what a panel of seasoned veterans would have surfaced. It really accelerates the timeline for acquiring expert judgment.
Oh, 100%.
So I want to leave you with one final thought to chew on today. We have spent this entire deep dive looking at how Gauntlet tears apart finished, published research papers. But if this adversarial multi-agent synthesis is this brutally effective at finding buried assumptions, flagging unrealistic latencies, and dismantling evaluation metrics.
Oh, I see where you're going with this.
Yeah. What happens if you point a pipeline like this at your own internal architecture designs and code bases before you ever start building?
That is a fascinating idea.
Right. What if, before you write a single line of code, your spec doc has to survive a review from Dr. Mike Roach and Professor Workloads? Could structured, adversarial, multi-agent pipelines be the future of automated red teaming for all system design?
It would definitely change how we build hardware.
It is definitely something to keep in mind the next time you sit down to draft a technical spec. Thanks for joining us on AI Paper Slop, and we'll catch you on the next one.